What attracts us to science fiction? One reason I think is that it deals with technologies and possibilities that are currently beyond our reach. Warp and hyperspace drives, characters are able to traverse the galaxy and quickly move from one star to another, teleportation technologies, anti-gravity, full optical invisibility, and so on.
There's one technology that appears very often in science fiction, but unlike all those that I just mentioned, it has existed and been used for quite a while. I'm talking about lasers. Sure, modern lasers probably would amaze someone from the mid-20th century, but not us. But we still want to be amazed. And here come lasers that are based not on light, but on gravity. More precisely, they're called Grazers, or gravity lasers. Well, yes, that sounds kinda crazy, but it doesn't mean that it's fundamentally impossible. Such things very well may be possible, could be created, and even occur naturally in the universe.
Even though lasers and masers are typically associated with something artificial, they in fact can naturally occur in space. And so, in this video, let's talk about lasers, about astrophysical lasers and masers that arise in the universe, and of course about strange gravity lasers, both as a technology and as a natural process.
My name is Andrei, and this is Cosmos Elementary. In astronomy, astrophysics, and in physics in general, lasers are used in a variety of ways.
Lasers were used to measure the distance to the moon, and regular measurements allowed us to detect that our natural satellite is gradually moving away from us. In laboratories, they're often used to create enormous temperatures and pressures, for example, to recreate, under controlled conditions, processes occurring in the depths of planets or even in stars, and also in other experiments.
Lasers could be used on various spacecraft,
as a means of communication between spacecraft, or on spacecraft like Grace 4 or Grail, which study the gravitational field of Earth and the Moon respectively. The laser beams on these paired spacecraft allow for the detection of minimal changes in the distance between them, indicating different effects of gravity on each spacecraft, when they are positioned over different areas simultaneously. This also enables the creation of gravitational maps of Earth and the Moon. The lasers on the Mars rovers, Curiosity and Perseverance, vaporize rock fragments, which allows spectrometers to analyze the vaporized material, and this helps scientists to determine the chemical composition of those fragments. Lasers are proposed to be used for propelling spacecraft using light sails, including interstellar ones. And there even have been some successful experiments here.
And there are many other examples. And it is strange to hear that lasers may arise naturally in the universe on their own. To understand how this is possible at all, we first need to discuss how lasers work. There are many types of lasers, and we won't delve into details of each one, but we'll touch on basic principles. As many of you may already know, that the word laser is an acronym, which stands for Light Amplification by Stimulated Emission of Radiation. The fundamental difference between the laser radiation and the light from a regular light bulb is that laser radiation is coherent, whereas the light from a regular light bulb is incoherent. A regular light bulb usually emits light in all directions. It's not focused in a narrow beam. And also, the light from a bulb is usually white or close to that.
So the radiation consists of a whole bunch of waves of different wavelengths, and these waves are emitted in various random directions.
And a laser emits a narrow, directed beam of light of a specific color, let's say red or green. This is not because there is a red filter that lets out only red light, but because only specific wavelengths are actually emitted. Laser emission is called to be monochromatic.
So ideally, there should be waves of only one wavelength. However, in practice, this is usually not the case.
The range is very narrow. It's just a small set of wavelengths, which gives us, let's say, visible red light.
Or green or blue.
But the light from a white light bulb or a diode emits waves from the entire visible spectrum.
In general, laser radiation is coherent, with a small frequency range and in one direction, and also with polarization, meaning that waves themselves are oriented in space in a certain way. In contrast, ordinary light bulb emission is incoherent. So this sophisticated type of emission can somehow occur naturally in space. In an artificial laser, however, it works like this.
We pump energy into an active medium, achieve population inversion, and then stimulate coherent emission. And now let's decode all that.
In the case of a regular light bulb, we have LEDs or incandescent filaments emitting light, and the light we receive is the end product.
In a laser, there needs to be a light source, but it is used only for pumping. However, pumping could be achieved via other methods as well.
Here's a simple illustration of how lasers work. At the center, we have the active medium. In this case, it's a ruby cylinder. But generally, the active medium can be solid, a gas, or a liquid. Here we have the light source to pump energy into the active medium, and on the sides, two mirrors, one of which is semi-transparent to allow the laser beam to escape. The mirrors create an optical resonator.
What happens inside involves quantum phenomena. We know that matter has a property of absorbing light, and it could get energy this way. And matter loses energy by re-emitting it back. But what is going on here at the atomic level?
Here is a schematic representation of an atom. At the center we have a nucleus made up of protons and neutrons and electrons around it. Here, for example, I've depicted just one.
Of course, in reality, electrons do not move in orbits like planets around the Sun.
Electrons exhibit wave properties, and we can't say at any given moment it is located in a specific space. Here, quantum mechanics fully demonstrates its weirdness, and we can only talk about the probability of where in the electron cloud the electron is located. And there are also different energy levels with average distances for specific orbitals. But for simplicity, we will stick to a basic model where electrons are represented not as spread out blurry clouds, but as points on orbits. However, in practice, everything is more complex. In an atom, electrons have a ground state with the lowest energy, and if an electron gains energy from somewhere, for example by absorbing a photon of light, it moves to a higher energy level. Moreover, to transition an electron in a particular atom to another level, a specific amount of energy is required.
If we're talking about a photon, then in a specific material, we will need a photon with a certain wavelength. If the wavelength is too long, it means that it has low energy and the energy might be simply insufficient.
And if there is too much energy, it's also not good. It can cause an electron to be detached, ionizing the atom.
The fact that the specific energy is required turned out to be quite useful in astronomy, and probably some of you have already guessed where I'm going with this.
Since certain chemical elements and molecules absorb and emit light at specific energies, we can use this to determine the chemical composition of various substances and astronomical objects. This is precisely what spectroscopy does, and what is reflected in those spectral absorption and emission lines. But let's get back to our lasers. We turn on the light source, which shines at the ruby rod, which, by the way, contains chromium ions, which give the radiation a red hue. Photons with specific energy are absorbed by electrons, exciting them and causing them to transition to higher energy levels. However, the electron cannot remain at this level for long because it always seeks to rid itself of excess energy and return to the ground state. Spontaneous emission occurs, the electron loses energy by emitting a photon back, and the electron jumps back to the lower level.
External effects can trigger this spontaneous emission.
Even vacuum fluctuations.
But notice that in a laser acronym we have stimulated emission and not spontaneous emission. And an excited electron can lose this acquired energy, not only spontaneously but also under the influence of another photon.
If a photon encounters an electron at a low energy level, it excites it. However, if a photon encounters an already excited electron, it pushes it towards emission, stimulating emission. Hence the term stimulated emission. But the most important thing is that the second emitted photon in stimulated emission will be so to speak, a copy of the first one, with the same frequency, phase, and even direction. That's how we obtain coherent emission.
But that's not all, and in what I described, there are actually a few more stages.
In the excited state, the electron is very unstable, and there is very little time before spontaneous emission occurs. So we most likely won't have enough time to first excite the electron and then immediately induce stimulated emission in this state. But electrons can first transition to a slightly lower level to a metastable state without emitting a photon, and at this level it can remain long enough for stimulation. This is also related to the fact that the pumped energy differs from the emission energy in the laser.
Another important aspect for the operation of a laser is population inversion, which I mentioned.
In simpler terms, in the active medium there should be more particles in the excited state than in the unexcited state. The state is called inversion because it is opposite to the usual state, where most particles are in the ground state. And when inversion is achieved, one photon stimulates the emission of another, and so on. And let's not forget that we have mirrors on the sides. The first photon were emitted spontaneously in different directions. But we need a directed beam. However, those emitted along the horizontal axis continue moving in that direction, stimulating the emission of new photons, which also start moving in the same direction, reflecting off the mirrors and effectively initiating a chain reaction of stimulated coherent photon emission. The distance between the mirrors is also selected not randomly but to allow the formation of standing waves of the required wavelength, which will reinforce each other. And the semi-transparent mirror on the one side allows the intensified directed beam of light to leave the device. This is what we see as the laser beam. As I have already mentioned, this is a simplified explanation. And also, instead of a ruby, a variety of different substances in different states of matter can be used as a medium, resulting in lasers with varying properties. Energy pumping can also occur not only through light but also through chemical reactions or electric discharges. There are many types of lasers. The laser emission can be not only visible but also infrared, microwave, ultraviolet, and even X-ray radiation.
And then there is gamma laser with the highest energy emission. And that definitely sounds like something out of science fiction. However, for now it's where it remains, because it hasn't been created yet. But the main thing is that now we can continue discussing space lasers, having at least a basic understanding of concepts like active medium, pumping, coherence, and so on. That will be useful. As I said, the principle I described worked not only with visible radiation but also with microwaves. The microwave counterpart of a laser is appropriately called a maser.
It's interesting that masers were actually created before visible light lasers, and it's more common to find maser emission in space. For it to occur, a process similar to the one I described in the previous part of the video needs to somehow repeat in the natural environment. We need an active medium, we need energy to be pumped into this medium, and we need population inversion to occur in this medium. Though it is unlikely to find a pair of mirrors or any other type of resonator floating around in space, but on Earth, lasers can be created including those without such resonators. Instead, sufficient length of a device can be enough. And when it comes to large sizes, there's certainly no shortage of that in space.
So in general, it's not surprising that under conditions where there is sufficient density of matter somewhere in space, with the appropriate dimensions or so-called active medium length, and where there is an energy source for pumping energy into the medium, maser radiation could occur. And, well, it does indeed occur.
It's interesting that when it was first detected through observations, it was initially thought that it might be emission from some previously unknown chemical element, and it was given the nickname mysterium. But then of course it turned out that it was not a new element, but where exactly can masers occur in space?
Let's test your cosmic intuition. The basic conditions I described: high density, size, and energy source. What could fit that description? If you're interested in testing yourself, pause the video and write a comment. Well, and here's the answer. Perhaps the most obvious candidate is the material near either forming or dying stars.
Stars form within molecular clouds made of gas and dust, where the density of material is significantly higher than the average across the galaxy. And the energy pumping can actually be done by the stars themselves. A similar situation occurs with dying stars, which shed their outer layers and can be surrounded by denser material. Energy can be pumped there not only through radiation but also through collisions between particles caused by, for example, shock waves, and even as the result of chemical reactions. Moreover, masers in such environments can originate from different molecules. By the way, the discovery of space masers became evidence in favor of the idea that in space, not only atoms but also molecules can exist. Before that, there was an opinion that this was impossible. From regions around evolved oxygen-rich stars, we detect maser emission from hydroxides, water molecules, and silicon monoxide. From star-forming regions, astronomers detect maser emissions from hydroxides, water, and, for example, methanol. Additionally, masers can be found in supernova remnants. Maser emissions, like in regular lasers, are coherent and directed, but in this case, they have different wavelengths. But in general, there are many sources of cosmic masers. Apart from stars at various stages of evolution, they emanate from comets, planets, and their moons.
But the most powerful masers, which even have a cool name, mega masers, are emitted by active galactic nuclei.
The material surrounding a supermassive black hole gets heated in an environment with high density, temperature, and a lot of radiation. At certain distances from black holes, mega masers are emitted.
And of course, detecting masers in space is not just about saying, wow, cool, lasers in space, pew pew.
I've already mentioned that the existence of molecules in space has been confirmed with the help of masers. They help obtain information about the chemical composition of various regions and objects. The narrow spectral lines of masers and their behavior allow for measuring velocities, sizes, distances to objects, as well as their masses. Also to reconstruct the distribution of matter in space and its movement. And in general, to learn a whole bunch of useful and important information about the objects of various scales, from comets to supermassive black holes. Well, masers are found in large quantities, but what about something more powerful? Not microwaves, but more intense radiation. Here, it is not as diverse.
I found much less information here in the case of masers. Perhaps it's because when I type in lasers in space, Google provides anything but what I'm actually looking for. But even with more specific queries like astrophysical lasers or with some other additions, the information is still quite sparse, even in specialized databases. The thing is that stimulated emission of shorter wavelengths is rare.
For example, I found a paper discussing the observation of infrared laser emission in the atmospheres of Venus and Mars. Here, carbon dioxide is involved, which absorbs solar radiation.
Perhaps the main example is the natural lasers at the star Theta Carinae.
A binary star surrounded by the homunculus nebula. This nebula is most likely the result of a powerful eruption and ejection of matter from a dying star at the center. It is called a pseudo-supernova because it resembles a supernova with flares and ejections, but in reality, one of the stars in the binary system has not yet died. So here astronomers discovered not just a laser, but a super laser. More precisely, here we are jumping from infrared through the entire visible range and landing in the ultraviolet. And this ultraviolet laser emission may be associated with powerful flares and ejections.
But as cool as it sounds, it's not even close to being as strange as gravitational lasers. Some might think that the idea of gravity lasers is related to something like...
I once had a video about a Kugelblitz, or about a black hole made of light. It sounds paradoxical. Black holes are associated with extremely strong gravity, yet light or photons are massless particles.
So what in the actual world, you might wonder?
Although photons do not have mass, they still possess momentum and energy. As we recall, Einstein said something about the equivalence of energy and mass.
So I've talked about it in my videos about photon engines and also about the black hole made of light.
The main point is that photons not only are subject to gravity and follow curved trajectories in spacetime, but they also exert a similar effect themselves. However, it is very, very weak, immeasurably weak, but it exists.
So one might think that gravity lasers are about something like that.
To concentrate a very powerful beam of light in order to induce a noticeable gravitational influence, but no. We're talking about something else.
So here the hypothesis is that similar to how we could create coherent emission from photons or electromagnetic waves, we could do the same from gravity.
According to Einstein, as we know, space is not just emptiness. It is a dynamic entity that is able to bend and curve. Einstein's general theory of relativity also predicted that waves could propagate through space-time. Their existence was confirmed in 2016. The collaboration of gravitational wave detectors LIGO and Virgo announced the discovery. And since then, many more events have been recorded. Primarily, these are waves from mergers of stellar mass black holes, but there have also been events involving neutron stars. Currently, we can only detect waves within a certain range of wavelengths, and they are precisely generated by such mergers, although there can be many other sources of gravitational waves. In ordinary lasers, photons are emitted, and again, for many it's not a secret that light has a dual nature. It can be described both as particles, photons, and as waves. And of course, this applies not only to photons, but also other particles as well.
For each of the three fundamental forces, there are corresponding carrier particles.
Photons play a crucial role in electromagnetism, gluons for strong nuclear interaction, and W and Z bosons for weak interaction. However, for the fourth interaction, gravitational, the existence of graviton particles is hypothesized. They're considered hypothetical because they have not been detected in experiments yet. Despite gravity governing the motion of bodies in space, planets, stars, and even clusters of galaxies, it is the weakest of the four fundamental interactions. A small magnet is strong enough to overcome the gravity of an entire planet.
The influence of an individual graviton is incredibly weak. Perhaps that is why it is very, very difficult or even impossible to detect.
Although we have already detected gravitational waves, the detection of that graviton particle would be a crucial step towards solving one of the main problems in modern physics, the unification of quantum theory and general relativity, possibly leading to the creation of the so-called theory of everything.
However, many scientists believe that they must exist. And if we want to talk about the possibility of gravitational lasers, we first have to assume the existence of gravitons. That's why such lasers are sometimes referred to as graviton lasers. And there begins the familiar story. We need to create a beam of coherent gravitons. For this, we again need an active medium, energy must be pumped into it, and also population inversion must occur. It's not just like a regular laser, but where could such a thing actually arise?
Here's an example. An article from 2018 discussing how black holes could act as natural graviton lasers.
As an active medium, wisps are proposed. These are particles that are weakly interacting with ordinary matter, and they are also proposed as dark matter candidate particles. Most of them are hypothetical particles, however, some neutrinos are also considered, and they are even mentioned in the paper.
Due to the so-called superradiance, particles near the event horizon of a rotating black hole can acquire angular momentum, and thus energy, from the black hole itself, effectively amplifying it. It is hypothesized that wisps may at first spontaneously emit gravitons, and then these gravitons could stimulate the emission of other gravitons, much like in a laser. Moreover, just like in a laser, a situation can be created where particles at higher energy levels become the majority, initiating a cascade of coherent gravitons. Mirrors may not be necessary here either, because for particles in orbits around black holes, paths can be arbitrarily long. These paths can be long enough to initiate stimulated emission of gravitons. So it turns out that black holes can indeed shoot gravitational lasers, Grazers.
As written in the abstract, quote, "To be in the path of particularly harmful amplified graviton death rays will not be pleasant." Indeed. And if we detect on our detectors narrow, coherent signals of gravitational waves, it could confirm that hypothesis.
Though it may take a while for particles to loop around a black hole in order for such a gravitational beam to form. The article provides estimates suggesting that even the current age of the universe may not be sufficient for such gravitational beams to form.
So it's not surprising that we haven't seen them yet. But perhaps one day, although...
But that's a hypothesis about natural gravitational lasers. There are also a few studies on creating artificial grazers. In this article, neutrons cooled to almost absolute zero are proposed as the active medium, acting as a quantum mechanical system and interacting with gravitational fields.
And to pump energy into the medium mechanically using vibrations of a specific frequency. This way neutrons can go to a higher energy level, population inversion could occur, and then coherent gravitons could be emitted.
In this article, a device for gravitational lasers on an undulator is proposed. When I listed types of lasers, I didn't mention another type, free electron lasers. In those devices, the setup is slightly different. The electron beam passes through an undulator, which is essentially a system of magnets where the beam undergoes oscillations and emits photons. Here, heavy ions or electromagnetic waves passing through a magnetic field are proposed to be used. In other words, gravitational lasers are created here using either particle accelerators or more conventional lasers. So far, gravitational lasers have not been created, and I haven't found any information about active attempts to create them at the moment. However, if they are possible, theoretically they could be used to expand our understanding of physics.
Thanks for watching. Links to all of the sources are, as always, down below in the description. And if you enjoyed the video, leave a like, comment, subscribe for more videos in future, and feel free to share this video with your friends, family, and everybody else. Okay, bye.